All right. Good morning, afternoon, or good evening, everybody. Welcome back to the point distribution webinar. Today we have Woden Kusner from the University of Georgia talking about measuring chirality with the wind. Woden?
Yeah. All right. Let me just set up some screen sharing here while I, say thank you. And I'm sorry I've been missing a bunch of things. Normally I'm traveling on these days, but I'm really glad to be here and see some familiar faces, and I guess also some other faces. I'm not quite sure what the audience here is like with their backgrounds. I think given that this is the points distribution seminar, I have sort of a general idea. This is maybe a little bit different. I'm not going to talk about, things like that you might expect me to talk about, which might be like, interesting particular configurations or optimization. But as you can tell from the title, I'm talking about some kind of measuring chirality. We'll look at some maybe interesting measurements we could make on bodies or surfaces. And I think it's a flavor that maybe a lot of people are familiar with. There's sort of an integral geometry, an average value type argument that we're going to try and get to at the end. All right, so let's see. Let me pull up the screen here. And so what do I really want to get with or get to? We're talking about measuring chirality with the wind. Well, there's sort of, there's a shape, right? We think of trying to measure shape as like a vague question. And we might break it down into something like, area, which is something that we're familiar with, right? Like we might think of projected area as like a very common kind of thing, right? Like you just, you take a random body in space, you want to look at what its shadows, like average area is. It's kind of a classic integral geometry theorem. I want to kind of take a different perspective. Let's not look at like the average area, sort of an average mass, but let's look at kind of an average, chirality, an average handedness, or an average torque. And that's going to be where we're going with this. I think I'll annotate this as, okay, what do we want to do? We want to measure some shape. Right, we're going to measure shape. And I guess some of the key points here to keep track of are, we're going to try and measure the shape of, well, curves in general, and we'll stick to R3. As you'll sort of notice, I've said torque a number of times. This is something that, we'll use some of the nice identifications in R3 to just, make sure that we're not mixing up sort of vectors and covectors and things like that. Okay, so that's sort of our plan. And we'll go into a little more detail with definitions just to start with. So I want to begin with this notion from Lord Kelvin, right? This is sort of my active learning part of the lecture or something. So this idea of chirality, right, which you might imagine will be key, was really, I guess, okay, I mean, it was sort of known to the chemists, in the 1800s, I guess. It was really starting to get explored there in the sort of English, UK field of science, right? This is really introduced by Lord Kelvin in the late 1800s. And it's basically, this definition persists, right? It's, if you have something chiral, if its image in a plane mirror cannot be brought to coincide with itself. Basically, it doesn't have a reflection symmetry. Okay, so there's no reflection symmetries. And, this kind of, what is this? Like, what are we actually measuring? Kelvin was looking at like a group of points. Maybe we'll look at bodies or curves in space. All right, and I want to highlight one thing here because I think, we process this definition, informally. And, you know, we usually think of this chirality and handedness, right, as meaning the same thing, right? Like, okay, you have something chiral, then it's, you know, then it has a handedness, right? That's something that I think we process, you know, when we're looking at this just, you know, from a sort of soft perspective. But maybe we should just, you know, take a second and say, okay, chirality is really about the existence of, you know, this split, right? You can break it into like a left or right-handed object. It's not actually assigning a handedness to a particular object, right? So just like you have maybe an orientable surface, right? That doesn't actually come with the orientation, right? So, you know, if you have an oriented surface, that's like having your handed, you know, a handed object. Being orientable is like being chiral. Maybe it's sort of like, if you want a rough analogy. And so that's maybe just something to not necessarily keep track of for this talk, but maybe to keep track of in general. All right, so we've given ourselves, you know, this base notion of chiral. You know, and this is something that, you know, you can probably figure out if a body is chiral. Like if a rigid body, you know, you can, you know, check a bunch and figure out that, okay, it has no mirror planes. You might be able to find some nice invariants. Think about, you know, just how the symmetries of this object work, right? Most things are going to be chiral, right? If you take some random point cloud or, you know, a random body, you know, with, you know, I'm not defining the measure that you're sampling, but some random object, it's probably going to not have a mirror plane, right? Or a mirror symmetry. That would be pretty strange, right? Okay, so here's one of my little exercises, right? We can, you know, sort of how we're worried about things. Okay, we can certainly break things up. We have chiral objects into these left and right-handed, you know, into these two groups, right? I mean, that's what being chiral means. So we could have sort of a left side and a right side here, where we have some mirror plane that tells us, you know, whether we're, well, in one family or the other. And we've got, okay, so, you know, left hands and maybe left feet go together, right? We've got something that has some extra symmetry here. My poor example here of a sphere. So this would be our achiral object. And then we get into some like slightly weirder things that maybe illustrate some of our ambiguity, right? This here is what, this is a right-handed helix, right? Just to go back, or at least we call this a right-handed helix or a right-handed screw, right? We can kind of use our right-hand rule and we rotate around and we're kind of going up in one particular direction, right? So, you know, right-hand rule here. And if we're an engineer, right, we take this kind of nice decorated surface here, and this is going to be a right-handed propeller because as you spin it and it moves through the water, it's going to trace out, you know, a right-handed helix. Right, sort of a point on it will trace out a right-handed helix. That's something to play around with if you like. And, you know, maybe I should, you know, well, if I had everything set up properly, I would poll the audience, but I won't put you on the spot, right? For the topologists though, what is this thing here? I'm pretty sure if I've done this correctly, this is a left-handed trefoil. Let's see, and I think you can see that by tracing out, right? Let's see, we go in kind of an orientation, right? We put an orientation on it right here, and there's sort of a left-hand rule here, right? If you know, do your kind of linear algebra, calc 3, you know, pointer fingers, you see you cross over and under following sort of a left-hand rule, say at all the crossings, Right? So this is going to be a left-handed helix or left-handed trefoil. And suddenly, okay, now we're extracting the fact that mathematics and definitions can be kind of arbitrary or conflicting, right? I mean, what's going on here, right? We've got a left-handed trefoil and also a right-handed surface on a trefoil here. And okay, really, what about something like this? Right? We got our potato here. What is this? Right? It's chiral, right? I mean, it belongs in one of these categories, I claim, right? Your general potato should not have a plane of symmetry, or it should not have a mirror plane, right? Or it should not be able to be brought into coincidence with itself through a mirror plane. So is it left or right-handed, right? And that kind of, okay, so what's the question, right? I'll ask is, right, is my left foot, left like my left hand? Right? I mean, my left foot and my left hand, we both call left-handed, right? Or we both call left, right? They both are on the left side of our bodies. But is there a way to actually say that they both belong in that same class, right? Are they both left-handed in some mathematical sense? Let me formalize that a little for us, mathematicians, and that's going to be basically asking, is there a measure, right? When I said it before, sort of, is there a discrete measure that maybe want to quantify like leftness, like something could be very left and something could be very right. And so you might ask, is there some, well, let's make it a continuous scalar measure, right? That's going to tell us, what belongs on the left-hand side, right? So let's make left-handed a negative value for this measure. Right? What belongs on the right-hand side, we'll make that something with a positive measure, right? And it would be really nice if, we were able to say, okay, if it's 0, then it's achiral, right? That there's a mirror plane. So it would be great if we had something like that. Because then you just go in, right? You take your potato, you put it in your chirality measuring machine, and it says, this is, this is, 50 left, right? And then, you put in your other potato and it's like, this is 50 right. And, you say, okay, well, this potato is really right-handed, this potato is really left-handed, and you put in your hand and you say, oh, well, that's a left hand. You put in your left foot and it says, well, actually, that's a right foot, at least from our measure. So everything is kind of messed up, but your right foot would be left and everything works out nice, right? We'd like it to kind of have that symmetry as well, I suppose. Okay, I just want to sort of check, like, we're on the same page here. We'd like something like this, or something like this would be pretty cool to have. Right? I think so. So obviously I'm setting us up for failure here. If something like this existed, it would be really fantastic and we'd probably all know about it. And answer probably lots of questions. But there's sort of a quick sketch as to why we can't have something like this. And this is sort of a notion of being able to deform our bodies or deform, whatever objects we're measuring through some nice space, right? Through some nice family of similar objects, say, immersed curves or surfaces or whatever you like, whatever we're actually trying to measure here. And it's sort of this idea of chiral connectedness. Basically, you can't have a continuous scalar measure that does this You'll notice I'm brushing over what continuous means again. Let's look at some nice topology on bodies, right? Like something like Hausdorff, use the Hausdorff metric. Basically, you can't have this kind of continuous measure because you can get paths from sort of left-handed things or to right-handed things. It's our paths from left to right, or paths from one body to its mirror image, right? That actually goes through only chiral configurations. And okay, now this is on one hand surprising, right? I think a lot of us, if we just kind of started with this problem, we would maybe begin looking for, okay, you always have to go through an achiral configuration if you're deforming like, something to its mirror image. That feels like a statement that could be true. But then, you analyze it a little more and you say, oh, well, okay, this actually really, this fails really hard in a lot of cases. And I'll just kind of give you an example. Let's say we start with two tetrahedra, right? We can make these chiral by, adjusting the edges appropriately. And sort of the naive argument is like, oh, okay, well, we have to pass through this kind of symmetric midpoint, right? This kind of like very regular tetrahedron, symmetric tetrahedron, because as we like move a point around, right, it's like, well, then suddenly like edges balance up, right? Yeah, there's some mean value that says, okay, yeah, this all works. But let me work in, not in polytopes, this actually, the argument fails for just pure, actual tetrahedra, but let me expand our space a little and I'll just add a decoration here that shows us, really why this fails in like the space of surfaces. Right? So let's just add like a little chiral, let me just add a copy of my left hand, right? And I'll just glue it onto this tetrahedron. And okay, so I deform, right? I deform my tetrahedron like this, right? I pop out the surface. So there's a little like, glove, out of that surface, right? I do my deformation now, right? This little hand is recording some kind of chirality, right? It's always going to be left-handed through this whole process, right? I do whatever deformation I was going to do to just fix my tetrahedron. Okay, and then I get rid of it, right? I shrink the glove down back into the surface. Okay, so this is a deformation of, my left-handed tetrahedron to my right-handed tetrahedron, and it goes through all chiral configurations, right? It's like I was chiral here. There's no way I can make this. Oops, sorry, is there a question? Okay, Peter. Okay, so this really shows that we can't really have all of these properties, right? If we have something that's continuous in this path, right? This is a continuous path. We've gone from left-handed to right-handed. We've gone through zero, right? We've gone from something that's a positive sign to something that's a negative sign, or vice versa. But we've avoided going through zero. So there's no real value, scalar value measure that's going to actually do this, right? So it's going to fail somewhere, right? One of these conditions is going to fail. And it's usually this last condition, right? This condition here, that's sort of the hardest, right, to deal with. And so actually, we're going to actually sort of, in the end, we're still not going to be able to address this, but we'll have some conditions that'll make us make the rest of this a little bit nicer, right? It's a nice measurement that we can make. Okay, so that's sort of the intro, just kind of like where things are, where things stand, and sort of the fields of let's say physical chemistry. Basically we want this measure so we can see if something is left or right-handed, and just put it in the machine. Sadly, this doesn't work because any measurement we make is going to fail some of the conditions that we want. And usually it's going to be that we're going to have something that is chiral, but comes back as achiral. Okay. That's sort of the status of things, and we're not going to resolve too much, but we are going to introduce a kind of a fun measure that's not a scalar measure, but gives us something, gives us a little more, right? It avoids some of these issues of passing through a single, having to pass through zero. Okay. And we're going to do this, or we're going to start with some hydrodynamic intuition, right? So this is going to be the measuring chirality with the wind part. And it's sort of this idea also goes back to Kelvin coincidentally, at least, in the, again, sort of the UK-based, literature. And the idea really is that right, things twist in the wind. If you take, some object, you hang it on a string and, you blow the wind on it, it usually twists. Okay. And we might formalize this a little, bring it into the classic kind of Landau, Lefschetz, Happel, Brenner, modern hydrodynamics. We care about how things move through fluids a lot. By basically saying we're in some viscous or some extremely inviscid flow. So, again, if you're into hydrodynamics, this would be kind of, it's unclear whether we're going to be at kind of the very low Reynolds number or very high Reynolds number. Are we falling through maple syrup, or are we falling through like a very non-interacting particle field, like, I don't know, like a photon field, something like that, where you have either a lot of friction and stuff kind of goes very slowly, or you have basically very little interaction at well, and you have pure scattering, right? But basically, this is, so there's a lot of literature in this area. Again, the idea is, okay, we've got some object here, right? We've got our little object over here. It's in, our fluid. We drop it, and it evolves and it does something, right? The object moves, right? It rotates, it twists. There's some torque on it from fluid interacting with the fluid. Something happens to it. Maybe it just falls straight down. But this is telling us something about the shape, right? We're measuring the shape by just looking at that, how this object moves in a fluid. So if we want to be, true physicists, right, then we just look at the equations of motion of a body in a fluid, right? This is some nice coupled, set of tensor valued differential equations, which are not completely understood, but make some assumptions. There's a lot of stuff that's solved. You can understand things, but it's not very fun from the point of view of like, soft analysis, right? It's hard to step back and like see what's going on there. And it's not like a good general tool, right? You say, okay, is this thing left-handed? And you take it, you drop it in. Well, it's a good physical tool, right? You take it, you drop it in some fluid, and you say, it's left-handed. But not so good from, analyzing on paper. But there's sort of a fun background motivational question, which is about, say, the existence of an isotropic helicoid. This is kind of a, this would be a weird edge case that would fit in with our sort of questions about measures, and also kind of fit in with hydrodynamics. So what is an isotropic helicoid? I'll illustrate by giving a non-example, which kind of, again, goes back to our question about left and right-handedness. If we have a screw, right? So here here is our screw or helicoid. And this is sort of known to the classical differential geometers, you know, and presumably to a lot of other people, but we forget it all the time. If you look at this helicoidal surface, right, from one particular direction, if we look kind of down the main axis, then this has sort of a clockwise, right? So in this picture, this has sort of a clockwise twist to it. But if we look straight down sort of into the board, right, we're gonna end up with sort of a counterclockwise twist, okay? Right, if you blow on it in that direction, right, if I blow down on this, it's going to twist counterclockwise. And if I blow a wind on it here from the right or from the left, it's going to spin in the clockwise direction. You know, and this is something that, again, we might all be aware of, but it's, you know, if you're not aware of it, it's kind of a, it's a little bit strange to think of, right? That all your, like the screws that you are screwing into the wall, right? You think, okay, righty tighty, lefty loosey, but if you turn your screw sideways, it's lefty tighty, righty loosey. Okay? Like same screw, you just turn it sideways, and you try to drive it into the wall, you know, it changes direction. You know, it's something to play around with if you like. If you've got some machine screws, you know, somewhere at home. Now, okay, that's the non-example for an isotropic helicoid. What would be an example? Okay, that would be something that if you know, blew on, right, from all directions, it always turns sort of in the same direction, right? So if it would be like a propeller that, you know, you could spin and it would work no matter what, right? It would always turn to the left or turn to the right. And okay, so maybe it should be something like this. You put a bunch of airplane propellers along the diagonals of the cube and, you know, everything kind of works out. And, you know, that would be like a nice sort of classical example. You know, who knows, right? Okay. Does that work? You know, question for the audience. Okay, so let's get to the meat of this. Right, so there's an archive paper, I think, that's linked on the seminar site. So this is work with Giovanni Dietler, Eric Rodden, Bob Kusner, and Piotr Chimczak. And we'll use this hydrodynamic intuition as our measurement tool, as might have been obvious, right? We're going to drop our potatoes into our maple syrup and see how they spin. Right. So we'll use our fluid as our measurement tool. And to avoid like the whole nastiness of really understanding the equations of motion, right? Let's just look at kind of the first order scattering, right? That initial rotation, right? That initial motion, right? So I take my potato, I carefully suspend it in my maple syrup, right? And then I release it and I see what happens in that first, you know, nanosecond, right? Does it sort of jerk to the left? Does it twist this way? You know, what's going on there, right? And I'm not going to care about what happens, you know, further along. That, you know, that derivative, right? That infinitesimal motion is going to give me some information about this object. Right? We don't need to worry about how it evolves at time. We'll look at that instantaneous twist. Right? So we'll think about that as sort of first order scattering. And I guess just to keep things simple, we'll talk about, you know, we'll use the example of curves in R3. R3 will be important, right? In general, the curves less so. For our setup, I want to use curves because the linear algebra is a little more straightforward, and I think the intuition is a little more straightforward, but there's sort of an analogous setup for surfaces and, you know, for bodies if you want. So what's our setup? Well, we'll look basically at a curve, right? So this will be our curve here. Here, we'll start with this curve, you know, x parameterized curve just because we love having parameterized curves. And we're going to zoom all the, zoom in. So we'll be at that point, XS, right? Where we can approximate everything, with just a line, right? We'll zoom in, we'll look at sort of that tangent space. And what are we going to have here? Well, I'll give ourselves our unit tangent vector, right? Our unit tangent, right? Calc 3, if we're teaching that, then this is all that good stuff. And we'll do a little bit of linear algebra, right? We'll give ourselves some constant vector field here. Right. It should be a constant vector field, so everybody's same length here. This will be V. And we'll observe that, okay, right, we can think about these as like little elastic particles, or I guess inelastic particles, right? Little hard BBs that are shooting out, and we're going to make our measurement there. So what's going to happen? Okay, when our wind hits the curve, right, it reflects off, and it imparts some momentum here. This will be some force FV applied to the curve just by, right, our particles reflect off. And what is that force? Well, it's proportional to V minus the tangent vector times the tangent vector dot V, right? You can just, this is a project, right? This is it's the other component, right? It's the complement of the projection of our vector field, right? It's just, okay, so this is just, linear algebra. You can break it out, and you can actually see this more easily maybe from, this here, rewriting this as the identity minus the unit tangent vector. So this is outer product, right? Outer product of itself. So we've got column row. Okay, so this is going to be a projection, and we're taking the component, sort of the force component of the vector V, right? This vector field V. So what does that give us? Well, okay, this will be that component of the force, but because we're doing linear algebra, right, we really can separate out the operator, right, this projection operator, I minus TT star, right, and apply that to sort of an arbitrary vector field, right, an arbitrary constant vector field. That's just always going to record the force that is imparted by that particular vector V, right? So we can actually bring out this operator here, right? This is the force density operator, and it's projecting V to the normal plane at X. Okay, so there's a little normal plane in here, right? And that's sort of a fairly straightforward computation. This operator is just a projection operator to the normal plane at that point X. Okay, so that gives us a force, right, at that point. And again, if we sort of remember how this stuff, how sort of our classical basic mechanics works here, this is a force, and we can apply that. We can think about this as being applied to a lever arm at that point, right? So the force is generating a torque around the origin, right? We've chosen the origin arbitrarily. It's given in our, it's implicit in our parameterization here. So we've got some lever arm to that point, and there's going to be some torque measured at the origin. Okay, and that's, okay, what is that torque? Well, it's, right, it's the lever arm, that's our point, that's the value of our point X, right, cross the force. Right? It's displacement cross force. We might worry about a choice of sign or something. Okay, but signs are all going to kind of get suppressed here anyway. Right? So left, right, plus, minus. So what is this here? Okay, we've got a torque measured at a point. This is also an operator, right? So this is actually an operator, right? X cross F sub V, right? And this actually has a matrix form, right? We can actually write this. Well, y. This is a linear form, right? This is some linear function, so it has a representation. Or sorry, the x cross has a linear representation, right? Which, if you sort of remember, and I feel like I keep saying like go back to linear algebra. I don't think I ever actually learned this in linear algebra, but I learned it somewhere, right? That you can think of taking a vector cross something as a linear operation, and it's this particular matrix. So if I want to take like x cross v, it's, right, I take this matrix and I multiply, right, by v. So something just kind of handy to have in our pockets. Because what are we going to do? Well, we'll notice that, okay, x cross here, right? This matrix here is a skew matrix. Okay, again, that's sort of like a basic property. Like you can get that from being a cross product, right? It's anti-symmetric. The cross product itself is anti-symmetric. So if you, and it's linear in each of its terms, right? In each of its arguments. So really this, the cross product operation with a fixed vector is a skew symmetric matrix. Right? So it's a skew symmetric operator. Okay, you've got this other linear operator here. F itself, right, is a linear operator. And you can kind of go back, it's projection, so and it's related to projection. So it's actually in the symmetric matrices, right? So what we have here is we have a composition, right? We have a composition of a skew matrix and a symmetric matrix, and that's our torque operator, right? Q here is the composition of x cross, the operator x cross, with the operator f. Right? Remember, our operator f is this guy here, or this guy here. And this means actually, this actually means that the trace is 0 of this operator q. And you can do this computation. You can do this like computationally, but sort of the slick argument is, right, that trace is an inner product on the space of matrices, and actually the skew and the symmetric matrices are orthogonal with respect to that inner product. That's right, one of sort of the tricks you might learn in the, sort of a continuing linear algebra, linear analysis course. And that's kind of interesting so far, right? What we have here is we have a trace-free operator that's floating around and it's measuring torque. Okay. Now this is at a particular point, right? This is at like a single point on our curve, but that's fine. We can actually integrate, right? We can integrate these operators on the whole curve to get, say, F and Q, capital F, capital Q. And these are both going to be symmetric and trace-free as well. And these are going to measure kind of the net torque, right? And the net force on our curve. And this is what I mean by integrate, right? We're going to just sort of find the net force of our wind, find the net torque of our wind on our curve. And I guess, we're getting into the weeds here, right? This is like getting a little bit esoteric, but if we sort of step back and just think about, okay, what is this thing Q doing, right? What is this big operator doing? It's kind of what I said. It's this net torque on the curve, right? With respect to some vector field, right? It measures, you put in a vector field, it kicks out a vector field and tells you the torque about the origin, right? I put in a constant vector field V. It tells you, okay, how does my body, rotate around the origin in that vector field? What was the initial moment, that initial moment in that vector field? And we can actually see, okay, this is a quadratic form, right? We can interpret this as a quadratic form, and it's going to measure the component, right? That's just extracting the component of the torque from a particular vector field in a particular direction, right? So if we take a unit vector here, right, this is the torque around the origin. We dot it with a unit vector. That's the component in the unit vector's direction of that torque, right? That's, again, sort of what dot product with a unit vector means. So really, the quadratic form UQV is the component of the torque about the axis defined by U through 0. And this is the torque coming from the vector field B, right? It's from this vector field B. In particular, right, if we look at this really, really as a quadratic form, that is, we take UQU, right? That's the twist in the direction of the wind, right? So that is what we think of. You take your body, you blow on it, and you see which direction it turns, right? So, or you look down, you take your potato, it's in your maple syrup, you let it go. Does it twist to the left? Do you see it move, like rotate to the left, or do you see it rotate to the right? Right? That's what QU or UQU is going to measure. And okay, so what is it? It's a quadratic form. It's trace-free. That basically tells us that we don't have to worry about sort of our coordinates so much. Basically, the symmetric part of Q is going to be the only thing that matters. And I'm going to sort of skip through a bunch of stuff here because this is more recorded for those people who are interested at some other point. Right. This also means you can solve most of the transformation laws fairly simply and get like, okay, if I change my origin, how does the torque transform, right? How does the force transform, right? If I rotate, how does my torque transform? How does my force transform? What I really want to get to is sort of what is the implication for this helicoid, right? This isotropic helicoid. And, right, what does being trace-free mean here? Well, let's think about like what happens with the eigenvectors of this matrix Q, right? And we can diagonalize this and we can just look in the directions of the eigenvectors. And that tells us, okay, the eigenvalues sum to 0, right? That means that they're either all 0 or there's some with opposite signs, right? They sum to 0. So that means, right, if we interpret this again, UQU is measuring the twist of the curve about an axis parallel to the wind. It says that if I've got a body and I measure it twisting to the left, right, there's another direction where it's going to twist to the right. Right? It's going to have, say, a negative eigenvalue. It also is going to have a positive eigenvalue. Twist to the right. And actually, on average, it'll be 0 twist. Okay? So this means that if you average over the sphere of all directions, right, there's no torque, right, in this wind. So this is kind of going back to, I think I mentioned, right, there's sort of an integral geometry picture here where you're trying to measure like the average surface area, right? The average surface area of like an object has some canonical description. Here, okay, this is the average twist in the wind of an object is 0. Right? Let's see. So we're kind of bumping up towards the end here. I'm not sure if we're supposed to, if I'm supposed to take the full 50 minutes or I'm supposed to give people a little time.
You can use the full 50 minutes or an early, either way is fine. There's time for questions afterwards.
Okay. So then let me give you one kind of interesting example, or one case study here, because I think some people, right, there's some people in the audience who might like approximations of things, or nice representatives of things, and there's sort of a backwards way to look at this too, where I kind of can give this. Okay, here's a nice example where we can do some computations, just by staring at it now. Right? Here we have maybe kind of two sails, right? One in the x1, x2 plane, one in the x1, x3 plane. So we've got sort of a vertical sail and a horizontal sail here. And we can just kind of, stare at this and see, okay, if I blow a wind, right, in the x1 direction, then this isn't going to rotate. Right, there's some symmetry there. Right, if I just blow on it, then this stays fixed. All right, so I can extract sort of the first column of my torque operator there as a matrix. If I blow in, let's see, the x2 direction, right, then I'm going to be rotating around the x3 axis, right, and I'm going to be rotating in some canonical way. And similarly, if I blow along the sort of x3 direction, right, then I'm going to rotate around the x2 axis there. Okay, so I can extract sort of the columns of my operator that way. And I can find, okay, what the eigenvalues look like too, right, or the eigenvectors and eigenvalues, right? So in one particular case, if I blow in sort of the 0, -1, -1 direction, right? So if I blow, like if my wind is blowing from this upper right, then you might see, okay, suddenly there's sort of this blue and red surface looks kind of like a propeller, and it's going to spin in a particular direction, right? And if I blow here from this kind of lower right, that's going to spin in the opposite direction with the same magnitude, right? So I look like a propeller of one-handedness from this 0, -1, -1 direction. And if I look at it from the 0, -1, 1 direction, it looks like a sort of a propeller that's identical, but its own mirror image. Okay, so sort of this surface here actually has its own mirror image living inside, right, living together with itself. And you can kind of compute the eigenvalues. You see they're equal and opposite. That sort of tells you, okay, there's one direction, I have a 0 eigenvalue that's in this x1 direction, and I've got these two eigenvalue or eigenvectors coming in sort of from the upper right and upper left. And you can use actually this kind of example to realize any torque operator. Basically, you can take configurations like this and get a representative that will behave in that initial torque the same way as sort of any torque, sort of any object. So it's kind of there's a representation with little propellers sort of in the standard, right, in sort of the standard basis of different sizes. You can build an arbitrary torque matrix that way, an arbitrary operator key. And okay, maybe that's a good place to leave off. I'll just sort of leave this picture here of this propeller, right? Here's something. How handed is this twisted propeller? It's both right and left-handed in equal amounts. It's twice as left-handed in one direction as in another. And you can do this by just some coarse symmetry arguments. Okay, so there's an eigenplane and a complementary eigenvector. Yeah, that's probably what I wanted to say.
All right, so thank you very much for the talk. I forgot to say this at the beginning, but as a reminder, so we'll have questions now, and then after questions, there will be tea time for anyone who wants to stay around and just socialize a bit. But yeah, do we have any questions for our speaker?
So you explained at the beginning that continuity, or this hypothetical measure, is
Yeah.
violated.
Yeah.
Right.
So here it's continuous, but yeah, this still fails actually. One of that last condition.
Yeah. So this tensor is going to be what? It's going to be continuous if you perturb the body a little bit.
Yes.
Right. But you can have two things that have that have zero tensors, and you add them up, and it's no longer. So, what's the right terminology? So you can have two things which are what's the non-chiral, and then you glue them together, right? And that becomes chiral.
Yeah.
In this
so
sense, it's
exactly. So this still fails actually this last condition that you want sort of zero only on achiral objects. And one way to see this is actually this kind of is from analyzing the eigenspace of Q. If you have something that has sufficiently high symmetry, so if you have like cubical symmetry, but you're still chiral, right? So you can just like add little decoration. So not the full cubical symmetry with reflections, but just right, sort of the SO3 subgroup. Then what happens? Well, that means that you have to have eigenvectors, right? Or you have to have equal eigenvalues sort of in 3 different directions, right? Like basically because you can, right, so the geometric interpretation of those eigenvectors is how you twist. So certainly you can sort of sweep out your eigenvectors by the orbit of that symmetry, right? That symmetry group. So it says that, okay, I have to twist to the left when I look from, this direction. I have to twist left when I look from this direction. I have to twist left when I look from this direction. It forces sort of all the eigenvalues to be 0. So you've probably seen like, they have these icosahedra or dodecahedra with like the little sort of twisted decorations on it. Right, so they have the SO3 symmetry, but not sort of the full they don't have the reflections. So yeah, there's
right.
Sort of,
I see.
There's a problem.
Like
yeah. So there's still a problem with this, and there's sort of a question actually, which I would ask some of the people here who are experts in like the sort of the function space and representation theory side of sort of the computational representation theory side of this, which is that like, can there actually exist some higher representation here, some higher tensor that can actually keep track of that information? Or do you always have this kind of trace 0 property that you can never detect this using sort of first order information? I think that's probably a hard question, although maybe it's super easy if maybe I had some idea, maybe it's just an immediate consequence of like Peter Weil or something, like everything decomposes into some very trivial set of things that always look like this.
But not.
Yeah, it seems like you want a good class of bodies to argue here. Like maybe if you restrict the picture enough, maybe something meaningful comes out, right? Because you can always ask stupid, you construct some silly fractals and then, okay.
Yeah, so actually how this works with things like fractal geometry is a little bit unclear as well. I think there's a way to interpret this, but it's right, having sort of fractional measure or something.
Right, the projection, the tangential projection thing kind of becomes very icky.
Maybe one nice thing though is that in most contexts, this is more really something that you can just like compute and do. Like, it's if you have like a nice discrete object and you just want to, say, how is this going to twist?
Yeah, like a point cloud or something.
Yeah, point cloud, exactly. You can just throw it on a computer. Point cloud's a little tricky again because of the you know, that you need to like, right, so sort of each dimension has its own little idiosyncrasies, like what does the projection mean? Like for bodies, you want to project to like the tangent space. For curves, you want to project to, you know, again, sort of the normal plane or the normal bundle. But, you know, I think point clouds, there is a way to kind of set it up, but, you know, it's kind of tricky. You know, also, you know, how does this work in higher dimensions, right? I mean, you know, there's sort of you lose the torque identification, right? But you do still have like, you know, I mean, you have sort of your covectors and, you know, some, you know, there are still objects that are floating around there, just that they don't identify as nicely with things like torque.
Right, you don't have cross product. Well, I mean, you won't be able to write things as nicely as in 3D because there are no cross products in. I forget exactly how it works. Is it like? Yeah, okay, I forget exactly what's the. Is it odd dimensional spaces? Or there are some subtleties about
I mean,
cross product, but it's not. Yeah.
Yeah, it's basically like 3 and 7 dimensions or something.
Yeah, something like that. Yeah.
Cross product. And the 7-dimensional cross product is not actually, you know, the right right. It gives you kind of a 3-dimensional space of like. So it's really only in 3 dimensions that you have a good cross product.
Yeah, but also this is not an issue of cross product as much as you'll have some projection operator, and you can probably still. It's just a matter of writing things up nicely. It's just. Yeah, here you got lucky because it's 3D. It's just a nice space. Okay, you have this operator, but then in principle you could.
We live in 3D, so you know a lot of this, or you know, sort of. Right. We're making our measurements in 3D. So if you actually want to do this with something, and this is actually kind of fun. So we actually 3D printed some like you know trefoil knots and stuff, and you can like you know put them in a little wind tunnel and see like you know. It rotates, you know, twice as much this way when you blow it, you know, blow in one direction, and it rotates sort of half as much, or, you know, twice as much as in sort of the other direction. So it's actually kind of cool.
Nice, yeah.
Other questions for our speaker? So if I was understanding, so I have a question. So if I was understanding, so chirality plays an important role in things with like fluid dynamics, or maybe that's the wrong word, maybe, but like how objects move through a fluid.
Yeah, so I mean, there's some of that.
What are some other places that maybe that appears in, if any? Just I've never really thought about this.
Well, actually, there's. So here's one fun thing, right? Like when you're doing these kind of astronomical surveys, right? Like, you know, people are looking for handed molecules because this is like signs of, you know, life or something, you know, it's like signs of some process, you know, that has a bias in a particular direction. So like our DNA, right, is handed. Yeah. So we're chiral, right? Like we're a process that creates, you know, sort of something that's kind of exceptional, right? We're unstable. Like we're not, if we were just, you know, completely, you know, wanted to have, if we were just a sort of a general chemical process that, you know, like a fairly soft, what am I saying? If we were sort of more, if we were kind of a low energy or sort of a low state thing, right? Like not this weird, like kind of, you know, like we were in some like very high energy state, right? Like humans and life in this planet, like, you know, we're very weird state, like very unusual, right? So we don't make like equal amounts of left and right-handed, you know, DNA molecules, right? So if light shines through us at a particular, you know, wavelength, right? This rotates the polarization, you know, sort of the polarization of the light, and you could see this in principle. Like, so if you've ever done, you know, if you ever there's like one of these experiments, which is you shine like circularly or planar polarized light through like sugar, and you can measure the rotation of this light, and you can say, okay, you know, we see that these sugar crystals have some kind of chirality in them, right? They're more left-handed than right-handed or something like that. Now, sort of the side effect, or one thing that doesn't get mentioned, is that this is sort of this is an effect of a particular wavelength, right? And so like on average, you know, what I'm talking about now and sort of what other, you know, it's supported by other theory and observations, right, is that if you sort of average over the full spectrum of light, you get no rotation, right? You know, so this means that, for example, some of these, you know, these astronomical surveys, you know, they have to be, or they should be careful about the way they're stating, we notice, you know, left polar, you know, that our light, you know, the light that we observe is polarized in a particular way, or, you know, we notice that, you know, it's rotated in a particular way. You know, what does that mean? Well, it might mean nothing, right? Like,
okay. All right, thanks.
Well, that's still a weird fact, right? It's kind of still weird that you look at this particular frequency and it happens to be localized in this particular plane. That's still a weird fact. So
yeah,
I mean,
it is.
It's a different story that, okay, you average over entire spectrum and you lose this, but it's still a pretty weird fact that this one frequency happens to be localized like that. There is no, I don't know, there doesn't seem to be any, there doesn't have to be a reason for that, right? But apparently there is.
Yeah, I mean, you know, I would interpret, you know, my interpretation of this is that, you know, the different frequencies are interacting at different scales. And so even if you have something that is, you know, like, okay, so I'm claiming that sort of on a very coarse level, things are kind of average zero, you know, but if you interact with, you know, this propeller on the page at sort of the wavelength of the long axis, you know, you might not interact with it at the wavelength of sort of this short axis here. You know, so it's like, I would expect that, you know, something similar is going on, right? That, you know, particular wavelengths are sort of picking out, you know, sort of different scales of handed or chirality, or handedness, I guess. You know, there's some other things too, like, you know, I'm talking about the actual particles, right? It could be that, you know, some measurements like light are actually interacting with kind of the bulk object. And there you get, you know, some handedness coming from, like, you know, it's sort of a different property. It's actually like the, I mean, you get sort of this you can get sort of this helicity that just comes from like an obstruction. Like, you know, you have a, like if you have like a singularity or something, this can kind of force you to be one-handed or the other in kind of bulk. You can kind of think about that, like if you look at, right, when you puncture the plane or something, right, and you want to have, you know, you can sort of curl around one way, you know, you can rotate around one way or the other. So like, you know, vector fields that, right, if you take out like an axis, right, then you might say, okay, you've got some objects, they're going to kind of be, well, either kind of bulk left-handed around this axis or bulk right-handed. You know, and I'm not sure how that actually interacts, you know, on that scale.
Any other questions? All right, well, I will stop the recording now.